Here's a few more problems. Find the 27th term of the geometric sequence with first term a1 equals 8 and ratio r equals 3/2. Round your answer to the nearest integer. Okay, so this is intended to be a pretty straightforward problem. We just turn to our master formula. Remember why this is true. This says start with whatever your starting term is and repeatedly multiply by r. Well, if you repeatedly multiply by r, that means multiply by a power of r. Why is it n minus 1? That's the number of steps in between a1 and an. So for example, a2 should just be a1 times r once, because you're just going one leap, one step from 1 to 2. And that's why, and if n equals 2, you're going to get r to the 2 minus 1 is r. So that n minus 1 is really because we start counting with 1 here. It's a little awkward, but it's fairly standard. So here it's really just plugging things in. a1 equals 8, r equals 3/2, that's given, n equals 27, so this doesn't literally say n equals 27, but the 27th term with our counting system, where you start counting with 1, pretty standard, is going to be n equals 27. And so we just plug it in. A sub 27 is 8 times 3/2 to the 26, because we started with 8 and we've gone 26 increments or steps from the first one to 27. And it turns out to be a moderately big number. It's not an integer because we've got these halves dividing by 2 each time, but it's a pretty big number. And that's geometric growth is like that. This is like starting with $8 in the bank and getting 50% interest 26 times compounded. That's pretty nice. You're going to end up with $303,000 roughly. Okay. Now here, this is supposed to be very straightforward, partly because I gave n here. But what if I asked you a different question? In the same sequence with a1 equals 8 and ratio is 3/2, I claim that there's a term of the form 3 to the 19th over 2 to the 16th. What's n for that? Which term is that? And this can be very, very useful and even pretty necessary if you're going to apply a summation formula to say the sum of everything from 8 up through this term. And so that's a very valuable skill. Well, what we want to do is we just want to match that. It should be of the form, if it's really in this sequence, if I'm not lying to you, should be of the form 8 times 3/2 to the n minus 1. Okay, so let's go ahead and match that. This is a very classic example of solving an exponential equation. In principle, I could kind of do it using logarithms, and I guess you could, but it's not a great way to do that here, because you shouldn't end up having n be anything but an integer. And if you did logarithms and got n equals 3.79, you're definitely in the wrong there. Okay, so we want to go back to more basic skills, which is express everything in terms of consistent powers. Oh, hey, that's 2 cubed, and that's 3 to the n minus 1, and that's 2 to the n minus 1. And let's combine that with rules of exponents. That's 3 to the n minus 1 over 2 to the, if I bring this down, it's really going to be a 2 to the n minus, to the minus 3 on the bottom. So it's going to be n minus 1 minus 3, or n minus 4. Okay, so this is just another way to write all the terms for this sequence, this geometric sequence. It's a power of 3 over power of 2, and the power of 3 is 3 ahead of the power of 2 on the bottom. Okay, so now I just have to match it. Oh, is there an n so that n minus 1 is 19 and n minus 4 is 16? Okay, that definitely is true, and n is going to be 20. And if this didn't work out, if the top was suggesting that I needed n equals 20 and the bottom was suggesting n equals 23 or something, then I would be lying. This would not actually be of the right form. But in fact, this is of the right form. One way to think about it is the powers would match top and bottom if it was just 3/2 to a power. The 8, that's a 2 to the third, is canceling out 3 of the powers on the bottom. So here n equals 20. And that could be very useful for example, a summation problem. Okay, let's do one more. I don't want to make these videos too long. Well, it's going to have various parts. Okay, write this using sigma notation. Do not evaluate the sums. Okay, so here's something written out in longhand, which, for my money, is more meaningful than the sigma notation at this level. But often we want to figure out how to write that compactly using the sigma or summation notation. So as I point out here, the main thing with these ones is to separate out into pieces. We've got a numerator, which doesn't look like it can be separated any further, but it looks plausible. 3, 5, 7. Okay, it looks like all the odd numbers starting at 3. We've got a denominator, which is written explicitly as powers of 2. Hey, that's a geometric sequence. I understand that. And then we've got some alternating signs. Okay, so the numerators, Those are the odd numbers starting with 3. Now, if you can always hit it with the general formula for an arithmetic sequence. Starting with 3, add 2 repeatedly, and how many times? Now, I'm going to use a k here. And the reason I tend to use a k for the dummy variable of a sum is I like to reserve n for a variable that actually has a meaning outside of the sum, not a temporary variable. And the book doesn't do that terribly well. So I'm going to use k here. And so the numerator at stage k, this is going to be the first term, the second term, the third term, etc. of the sum, is just going to be 3 times 2 times the number of steps between 1 and k. Simplifies to 2k plus 1. And as I say here, very common sequence, worth memorizing. Odd numbers, if you start with 3, is 2k plus 1. Okay. If you want the odd number starting with 1, which is a little bit more natural, and you start with labeling it by k equals 1, you're going to use 2k minus 1. Very standard. Okay. Now the denominators, 2 to the 1, 2 to the 2, 2 to the 3, pretty much given to us as 2 to the k. And the standard pattern for the signs, to get an alternating sign, which is a super common pattern of signs, is just minus 1 to a power. And if you want it to start with a positive, which it does, is plus 3 halves, you don't want it to be minus 1 to the k, because then when k equals 1, you get minus 1. The standard way to do that is minus 1 to the k minus 1. Okay, so all told, it's the sum, and I'll talk about the decorations on this in a minute, of minus 1 to the k minus 1 times 2k plus 1 to get those odds over 2 to the k. Now we chose the letter, which I chose to be k. You don't have to, but it's a good letter. We chose to start with labeling them with 1. That's what meant this had to be 2k plus 1. That matched up very nicely here. This was 2 to the k. That's all set. And then we just have to figure out, okay, what k is this? Well, we can't just explicitly count it because we've got dot dot dots here. But usually you'll be able to match this up with the master formula you've got. Oh, this was all the powers of 2 up to the 50th power. Okay, so here the k is exactly the label of the power, and you get 50. You can double check it by saying, okay, if I put in k equals 50, do I get a 101? You bet. Okay. Otherwise, if that didn't match, kind of like what we were just talking about in the previous problem, if this ended up with like a 107 over 2 to the 50th, that actually doesn't follow this pattern. They'd be lying that, or they'd be talking about a much more weird, confusing pattern. This pattern definitely seems to lead something that needs to match, where the 50 here matches the 101. Okay. One thing that I was seeing a lot in homework, and I've seen over the years, and I don't think I mentioned in class though, is something like just writing it like this, with the summation symbol, and then equals, and then the rest of it. Okay, so the misconception there is thinking that the summation symbol itself has a meaning. This is like a function. It's like the sine function, or the cosine, or the exponential function, or the logarithm function. It doesn't have a value itself. This should be read as the sum from k to 1 equals 50 of, with a very pregnant pause after that. There's no meaning to saying the sum symbol equals something. It's the sum of this whole thing. It's an operator. It's a function that eats a formula and says, put in all of the numbers from 1 through 50 into this formula successively, and then add up all the results. So you don't want to have this on the left-hand side on its own. It has no meaning on its own. It's something that needs to eat an expression to create a sequence. A little bit of a sophisticated gadget. Okay. What about this one? B, the first 30 terms of 1,000 plus 999 times 2 plus 998 times 3 plus 997 times 4. Okay. And I don't put a last term here, but what I do say is exactly how many terms there are, which is actually nice. Okay, so we're going to use letter K. We're going to start from k equals 1 because we don't have any particular reason not to. And we're told to end with k equals 30, basically. That's the way to get 30 terms. So that's nice. So here, it's actually a little easier to get the setup for this part. We know it's going to be 1 to 30, as long as we choose to start with 1, which is pretty standard. Okay, so once again, though, it's two pieces. We've got a descending sequence, 1,000, 999, 998, 997, and the ascending sequence, which is really, I can put in a times 1 here. Okay, 1, 2, 3, 4, 5. So that part is just k. And then, again, you can use the standard mechanism of an arithmetic sequence to recognize that 1,000, 999, 998 is an arithmetic sequence. It's not too hard to see that it's just 1,001 minus k. Notice it's 1,001, not 1,000, because we want to start with k equals 1. And 1,000 minus 1 would just give you 999. Okay, so the first piece is 1,001 minus k. and the second piece is k, and there's our how to write it as a summation. That can be useful for this problem. We haven't actually got any shortcuts. There are shortcuts for something this complicated. And sometimes we talk about this. I haven't this year. But this could be useful to put into to tell you how to put it into a calculator, for example. It's not hard to put in a summation like this into a calculator. So that'd be one of the values of this. Okay. One last thing. Let's do an extra. How would we put this into summation notation? So, and if you don't want to watch the extra, then just go take a break. Okay. So here again, it's sort of like part A. There's a numerator, which looks like it's following its own pattern. A denominator, which is following its own pattern. An alternating sign. Ooh, okay, and that is starting with a minus. So we'll start that with minus 1 to the k. We'll just go ahead and set up the summation. Let's go ahead and start with k equals 1. Okay. And I'm not sure how far it goes. I've not been told explicitly. I'm going to have to do a little pattern match. Okay. Now let's see, the bottom, well, they're both fairly standard sequences. The bottom, it's arithmetic. 5 minus 2 is 3, 8 minus 5 is 3, 11 minus 8 is 3. Okay, so it starts with a 2, and then it's 3 times k minus 1. Okay, I can make that a little prettier. That's going to be minus 1 plus 3k, or 3k minus 1. Okay. But I got it out of the standard formula for an arithmetic sequence. Okay. On the top, it looks geometric. 5 times 3 is 15, times 3 is 45, times 3 times 3. Okay. And hopefully this works, and we'll check that. So that's going to be 5 times 3 to the k minus 1. Okay, we're pretty much set. We just have to figure out what the top value of k is, and that's not too hard. We've got a general formula for, let me call that n. I like to call the last value n, because k is reserved for a temporary value that can take all the values between 1 and n. If you worry, if that doesn't make a lot of sense to you, I wouldn't worry too much about which letter you use. 3n minus 1 is supposed to be 29. Okay. So 3n equals 30, n equals 10. Okay, so there's 10 terms in this thing. And then we really should do a double check and see if they're really confusing us by putting something in there that's wrong. But we can check. I hope I did it right. 5 times 3 to the 10 minus 1, yeah, 98,415. I just evaluated that. So this is indeed correct.